Okay, so now we're going to graph polynomial functions. Now to some degree, you've already done this. Obviously, y equals x squared plus 2x plus 3 is a polynomial function of degree 2. And Algebra 2 is all about learning how to do that. Same thing, y equals x cubed minus 3x squared plus 6, a cubic function. Algebra 2 is all over that. But we want to be able to graph any polynomial function now, and we looked at the most basic form, the monomial function, last time or a few days ago. So y equals x to the 5th. So this is a monomial, and we might have a 2 in front. So this is a monomial function that shares a lot of its behaviors with the cubic function because 5 is odd and 3 is odd. They share a lot of the same behaviors. But what happens when we start adding all this other gobbledygook? And so we clearly do not want to graph these graphs by plotting points. We didn't even like plotting points for lines. So we're certainly not going to want to plot points for these unless we're able to find the exact right point to give us information about the graph. So let's look at an example real quick. Suppose I tell you I have a polynomial function that looks like this, right? We have no idea what that function is, but I could graph this if I knew the two maximum values. So if I could specifically plot the two maximums, the two roots, the turnaround, and if I could predict the end behaviors, then I would be able to graph this graph without having to plot all the extra points inside of there. So even though we certainly don't want to plot points ever, the more complicated a graph is, the more we want to reduce it to the minimum number of points. In this case, I would need 1, 2, 3, 4, 5 points and information about the end behavior to graph. So let's start by generalizing the polynomial function. They look like this. F of x equals some version of ax to the nth power, that's what we learned when we talked about monomial functions, plus some other ax to the nth power, because this is what polynomials are, right? Ax to the nth power, on and on and on. Okay, until we end up with some constant c. All right, this is not going to do because this implies that every polynomial function has exactly the same terms repeated over and over and over. So the notation that we're going to use is we're going to say that the first term has an nth power and the constant is a sub n, saying that that's, the coefficient, saying that that's the coefficient that goes with that n. So for the second one, we're going to write x n to the, when we write in descending order, right, this will be n minus 1, and so the coefficient that goes with that is going to be identified as the n minus 1th coefficient. The next variable would be the first one take away 2. This is how we write descending order, and so that would be a n minus 2. So that means I'm talking about the coefficient that goes with the n minus 2th term. And then these all have plus signs, and remember, if a is negative, then it would be a negative or a minus sign. And this goes on and on and on until you get to the, generally we write the quadratic, linear, and constant term. So that would be the a squared x squared, that would be the quadratic term, plus the a to the first, a1, a sub 1, x to the first power, plus a sub 0 x to the 0 power, but x to the 0 power is just 1, so we write our constant as a sub 0. So this is the notation for a polynomial function, and it just means this can go on forever and ever and ever. We don't ever want to deal with a polynomial to the 1832nd power, but if we had to, we'd know the polynomial that it defines. It defines every descending power of x and the coefficient that goes with it. So this is the generalized notation. Luckily, when it comes to graphing, we don't really need to know what all of these are. So first piece of information that comes from graphing is the n and the a sub n values. So this is where we talked before about the behavior, the end behavior of n and a sub n. So if n is even, we know that the end behavior mimics the simplest even function, right, the quadratic, and the end behavior goes off to infinity on the right and off to infinity on the left. Okay, so that's the behavior, or that's the information we can get from the function without having to plot points. If the coefficient is positive, then that is true too. Let's set up a table. I think that might be an easier way to do this. So if n is, let's say, even odd for our n values and positive negative for our a sub n. Okay, so if the power is even and the leading coefficient is positive, the end behavior looks like that. Okay, if the power is even and the leading coefficient is negative, it just means flip down like this. And we've seen that, right? Even power is a quadratic, and if the leading coefficient is negative, it tells us to flip over the other direction. If n is odd, like a cubic function, the end behavior looks like that, right? Looks like this, goes up on the right and down on the left. And so if a sub n, or if the leading coefficient is negative, then this function would flip over and be the opposite. So already we kind of have some understanding of what's going to happen to some generalized function, polynomial function. If we're lucky enough that the function we're talking about turns out to be a monomial function, and we talked about these before, then, and the reason I say lucky is all we know is end behavior for a monomial function, and our parent translations work. So if I have, for example, so we have end behavior plus parent translations, I should say transformations, because transformations includes both translations and dilations. So for a monomial function, that's enough. So y equals, let's make this tricky, 3x plus 2 to the 5th power minus 7. So it gives us all of our transformations. Well, the parent for this, right, the parent is y equals x to the 5th, and we know that y equals x to the 5th behaves a lot like y equals x cubed because it has an odd power, and so we know that the parent is a positive odd, so it goes this direction. So the end behavior, it's going to do something like that. It's the y equals x cubed, but it's going to stretch out kind of at 0. So then all I have to do is take that and play with it using the translations. So I would say, well, let's change this up a little bit. Let's put a negative here just so I can give every translation. So the first thing is I know it's going to flip, and the end behavior is going to look like that, right? I also know that the place right here in the middle is going to go backward to 2 and then down to 7. And so the whole thing is still going to go like that, right? Except before it does that, it's going to flip over and have a squeeze of 3. So the whole thing is going to squeeze together a little bit and go this direction and then up like that. Okay, so I can actually kind of sketch that graph pretty well, labeling this point, because if you plot a point, you have to label it, -2, -7. And then if I need to know a y-intercept or an x-intercept, I can use basic algebra to do that. So a monomial function, in behavior, parent transformations, we're done. But after a monomial, it gets trickier. So our first consideration for graphing a polynomial function is to look at in behavior. Done. Our second consideration then, using the function to kind of sketch in that graph, is to look at the power again. All right, so all we care about is n at this point again. And the information n will give us is twofold. It'll tell us, one, how many roots, maximum number of roots. So max number of roots, right? Roots are just x-intercepts. And it'll tell us the maximum number of turnarounds or turning points. All right, so if I were to sketch that, if I went up, down, up, down, up, right? And if I said this was every possibility for this graph, I'd be able to say this is a 1, 2, 3, 4, 5, right? It would be an x to the 5th power. So the maximum number of roots or x-intercepts equals n. That's the maximum. And then the turnarounds would be 1, 2, 3, 4, very interesting, equals n minus 1. Now, you're not always going to have 5 roots for a 5th power. Special cases that could happen, you could have 1, 2, 3, 4, 5. A graph could look like this, where you have your n minus 1 turnarounds, 1, 2, 3, 4 turnarounds, but I only have 1 root. Okay, so all kinds of combinations can happen. Another combination or another possibility could be up, down, up, down, up. Well, for that one, it's got to go up from there. So now I have actually 2 roots because one just touches and turns around. One of my roots is a turnaround, and I have 1, 2, 3, 4 turnarounds and 2 roots. So there are all kinds of possibilities. Another possibility could be up 1, 2, 3. Hang on. 1, 2 turnarounds. Okay, that's exactly what I was trying to do. So in this case, 1 root is showing, and I only have 2 turnarounds, but this could still be an x to the 5th, because all I know is the maximum number using n, but still that's useful information. All right, so this would be a good time for an example. So example 1, we're going to evaluate, for the purpose of graphing, the function h of x equals negative x to the 4th minus x cubed plus 2x squared. All right, so first thing, we want to look at in behavior. Well, it's an even power, so the in behavior is going to mimic a quadratic, and it's a negative coefficient, so it's going to mimic a negative quadratic. So the in behavior is going to go down and down. Okay, if I wrote this in limit notation, and you have to be able to do that, the limit as x values approach negative infinity, that'd be this side, equals O of f of x equals negative infinity. So y values are going down, 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 and the same thing on the other side, the limit as x values approach positive infinity of this function equals negative infinity. Okay, sometimes the arrows will be sufficient. If you're asked to put it in limit notation, it needs to be limit notation. Otherwise, just use the arrows. Okay, usually when I'm graphing, I'll just have you do the arrows, and if I'm having you evaluate, I'll have you do the limit notation. All right, so the in behavior we know. Next thing we know is there are maximum number of roots equals 4. And we find these by factoring. So if I factor this, set it equal to 0 and factor. So I have, let's see, x squared can come out. And I'm left with, let's take out a negative x squared so I can get rid of that leading negative. Negative x squared, so I'm left with an x squared plus x plus 2 equals 0. And I can continue to factor. This is x plus 2 times x. Hang on. Mistake found right there. If only I could erase it. So this is minus 2. So x plus 2, x minus 1 equals 0. When I find my factors, I get x equals 0 from this factor. I get x equals 2 from this factor. And I get x equals 1, sorry, x equals negative 2. From the second factor, x equals 1 from the third factor. So I actually got 3 roots. 4 is my minimum, but I only got 3. In point of fact, this is actually a repeated solution. Let me, because we tend to take the shortcut and say, well, this one equals x equals 0. But let's go back and do it more specifically. I'm going to say negative x squared equals 0. Now I'm going to solve. So x squared equals negative 0. Take the square root of both sides. X equals plus or minus the square root of 0. So x equals plus or minus 0. Okay, all of that seems like a bunch of gobbledygook because x still equals 0. But notice that really if I carried out the algebra on this instead of just the logic, I would have had a repeated root. So 0, I get negative 0 and positive 0. Even though it's redundant, what that means is my roots are, my 4 are x equals plus 0, minus 0, negative 2, and 1. I have 4 roots. But what does it mean when I get a repeated root? And sometimes you'll get an integer for a repeated root. It just happens to be 0 on this problem. What that means for the graph, and it's very important information for graphing, is what that means is when you want to make the graph of this function, we know the end behavior comes up from negative infinity, and I'm going to guess a little bit on the actual graph, so I'm going to dot it in, but it means that it's going to come up. So let's see, I've got a root at negative 2, so it's going to come up to negative 2, right? And then it's going to turn back around and come down to 0. That's the next root I encounter. And since it's a repeated double root, it means it's going to come and touch and turn back around. Okay, it's going to come and touch and turn back around. And then I have to have a root at 1, which means it's going to immediately turn back around and cross at 1. Okay, and the part I guessed at, I'm really positive about the roots, right? I'm really positive about the fact that there's a turnaround in the second quadrant and that there's another turnaround in the first quadrant. I'm positive about that because it's the only configuration that lets me have these end behaviors and these roots, including the turnaround point at a root, but I just don't know where this part is. So I could actually sketch this in and sketch this in because I'm pretty positive about both of those. And the only thing I don't know is does this go way up? Does it just barely go up? Yeah, I just don't know. So I dot it in. That's what I do when I'm not sure. And the truth is you have no way of knowing finding this turnaround point unless you use guess and check. That's a calculus thing. You're welcome to go ahead and sketch it in and just call it whatever you call it. I'm not going to mark you off for that, but I find it's more helpful to put in the dot so we remind ourselves we don't really know where that graph turns around unless we put it on a graphing calculator. And then the last directly related to the formula piece of information that is useful is to find the y-intercept. Okay, and when you want to find the y-intercept, the cool thing is, and I'm actually going to erase that because I don't need it. If I look at the original function, back up here again, the y-intercept is always wherever you plug in x equals 0. So it doesn't matter how many terms I have in my function, every single term will become 0 at the y-intercept except for a sub o. So a sub o is the last piece of information that you get directly, a naught we call that, which is the constant in the polynomial, is the y-intercept. Okay, so let's look back at the graph of the example we just did. If I wanted to find the y-cept, right, it's a sub o or a naught, and in this function I didn't have a constant. There wasn't a constant, right? So my intercept, when I put in a 0 for all my x's, I just get a 0 out. And look, that's exactly what I got. It was my turnaround point, and that is where I crossed the y-axis at 0, 0. So you get information directly from the function. That's the third information you can get directly from the equation. After that, you have to do some strategic point plotting. So the fourth piece of information, and our least happy, the one we like the least, is plot points. And the only reason for doing that would be choose a point kind of halfway between these two roots, and if it tells me that it's way up here, or if it tells me that it's way down here, it gives me information about that dotting in. The problem with that, though, is it doesn't really give me enough information. I don't tend to like to do that. I like the dotting in. So let's make a new decision about how you'll show your work. If you want to plot points to kind of see where the graph lives, and you can't assume that it's the maximum point, if you want to plot a point to see kind of where the graph lives, then you have to actually calculate a point. If you're not sure and you don't want to calculate a point, so in this case you would have something that looked like that. If you're not sure and you don't want to do that, then you have to dot it in, saying that you don't know how high that is. So let's make that deal. You can dot it in and skip the calculate a point unless I ask you specifically to do that, or you have to calculate a point if you want to try to draw your line solid. So quick review. Where have we gone? It doesn't matter how ugly a polynomial graph gets. You can get most of the way to a perfect graph just by using information that's in the function given to you. You start by using the power and the leading coefficient to determine end behavior, and the end behavior of an even function mimics the end behavior of the simplest even function, a quadratic, and the end behavior of an odd function mimics the simplest odd function. I use cubic just because I think it's more meaningful, but truly the simplest odd function is y equals x. And isn't that just this line that goes like this? But doesn't that have the same end behavior as the odd function, the cubic odd? So I tend to use the cubic as the simplest only because it gives me the curves that I need to kind of imagine the other turnarounds. But any odd function has this end behavior. Whether the leading coefficient is positive or negative changes the end behavior because it flips the function. The next thing we get from the polynomial is we get how many maximum number of roots and maximum number of turnarounds. So once you have that, it's pretty, sorry about that. Once you have that, then you can start looking at what must be happening in the graph somewhere. Then you can look for roots by factoring or using the quadratic formula or whatever. Solving the function will give you the roots. Combine that with end behavior, the location of the roots, and you know where the turnarounds are. Finding the exact value of the turnarounds is calculus, so we're always going to be sort of guessy-checky at this point of the game for that, but you have enough information to kind of do a fair sketch of the graph. You also can find the y-intercept wherever that is because it is the constant or the a sub o in your function, and then worst case scenario you have to plot some points to see what's going on in any particular region.